All right, folks, welcome back. We are going to do a paper reading of blip. We just covered clip. If you recall, a clip is a way to jointly embed images and text into a common vector space, semantically aware vector space, because of the contrastive learning, right? Now, this paper takes the idea much further. It says, and what it says is quite interesting, and it has a beautiful architecture. I would like to just read it out first to quite a bit, and we'll take it from there. The abstract says vision language pre-training. So now let's look at the wording. After clip, the word vision as a language, VIT and so on and so forth, visual transformers, etc. These sort of words became quite common. A vision language pre-training. Why? Because when you train with a lot of data, what you get is a pre-trained model. VLP has, and this is a new terminology or acronym for your vocabulary, often used in research now. VLP has advanced the performance of many vision language tasks. However, most existing pre-trained models only excel in either understanding-based tasks or generation-based tasks. So this is a statement that needs dwelling upon. It says that most existing pre-trained models only excel in either understanding-based tasks or generation-based tasks. You realize that when we create semantic and embedding, that sort of understanding-based task, right? It figures out the encoder. It's very much the encoder part of the architecture. It understands the meaning of the input. Remember, think of our language model diagram. Encoder produces a latent representation, a language model, which gets the decoder decodes. So who understands the text? Primarily the encoder. Who deciphers the text and generates something new? The decoder, primarily, right? So those are the two wings. And what they're saying is most existing pre-trained models only excel in either this or that, which means that they are either much more on the one side, encoder side, or the decoder side. Furthermore, performance improvements have been largely achieved by scaling up the data set with noisy image text pairs collected from the web, which is suboptimal source of supervision. What in the world is this statement saying? What it is saying is the way people have tried to improve these models, for example, clip, right, is by just making bigger and bigger models, right? Taking a bigger encoder, vision encoder, bigger text encoder, and doing, right, successive generations of clips and more data. But when you take more data, it points out by scaling up the data set with noisy image text pairs collected from the web. So that's quite a critique of the data set that goes into training these models. It says those are noisy. Noisy means lots of mistakes, lots of errors. And of course, which is suboptimal source of supervision. What does that phrase mean? Anyone? Means if you do supervised learning, supervision means this here stands for supervised learning. If you do supervised learning with a data set that's quite noisy and full of errors, you will get suboptimal results, isn't it? That's all it says. Now comes the, so they said that this is the backdrop. They're saying this is the reality at this moment, right? And now comes what they have to contribute. They say, in this paper, we propose blip, a new VLP framework, VLP standing for Vision Language Pre-training Framework, which transfers flexibly to both vision language understanding and generation tasks. And this statement is crucial. They're saying you can do not just, so remember, clip was more the understanding part. There was no generative aspect. In this paper, we propose blip, a framework, which does both vision language understanding as well as generation tasks. Right? So that's when you sit up and say, something interesting is going on. A blip effectively utilizes the noisy web data by bootstrapping the captions. What could that be? Okay, we'll see what it means. Where a captioner generates synthetic captions and a filter removes the noisy ones. So what it says is that you start with the captions that you got from the web. The alt text of the images. You start with that data. But one of the byproducts, one of the consequences of this architecture is that because it's generative, it will actually fix the caption. It will know that you're looking at a bird. Are we together? So a part of the things that it will do is not only learn from data, but it has a way to go bootstrap from the data and go fix it, right? Which is quite a thing. And in some sense, you can say this paper could easily have been two different papers because there are two different pieces of technology that it brings in, right? But we'll see that. A blip effectively utilizes the noisy web data by bootstrapping the captions, where a captioner generates synthetic captions and a filter removes the noisy one. So there'll be a captioner and a filter that will say, okay, this is just bad. Let's throw it away. We achieve state-of-the-art results on a wide range of vision tasks. And this statement is interesting. The wide range is the important part of it. On a wide range of vision tasks, not just understanding or generation, but a pretty wide range of it, such as image text retrieval. So what is image text retrieval? Clip was the image text retrieval engine, isn't it, guys? Primarily. With a 2-point recall at, so this is the level of improvement, not the actual, this thing achieved, such as image retrieval, image captioning, ability to caption images, and a visual question answer. Like I show you a picture and I say, what is this? Right? So you should be able to answer. Do you see a dog here? A blip also demonstrates strong generalization ability when directly transferred to video language tasks in a zero-shot manner. Code models and data sets are released. By the way, that, frankly, and it's my opinion, I would discount it. Right? It just says that, see, the video is made up of images, right, and audio. And so, well, if we can do images, we can also do video. Yes and no. Video also has a lot of temporal information. Right? So that last thing is true, but though I would say that you can, in my opinion, discount that part. So we go into the architecture, and this architecture is after what we have been through. So let me warn you before I show you the picture. The architecture is complicated, but I also would claim that if you have been following along, it will look to you easy. And I'll set the grounds for it in a moment. Right? And most of the important things are said in this page itself. In the first page, it says, vision language pre-training has recently achieved tremendous success on various multimodal downstream tasks. However, existing methods have two major limitations. So the first, from a model perspective and from a data perspective. Model perspective, it says, most models either adopt an encoder-based model. What's an example of an encoder-based model? In Clip, right now we did, right? BERT, of course, is for words, but if you're taking vision language models, then Clip is a classic example, right? But of course, in just pure NLP, BERT is an encoder-based architecture, yes. Either adopt an encoder-based model or an encoder-decoder model, right? So, for example, BARD is an encoder-decoder model. Right, and so on and so forth. So, however, encoder-based models are less straightforward to directly transfer to text generation tasks. Encoders produce what? By nature, they are about understanding. You can actually shoehorn some generation on top of it by just saying which is predict the next word from the dictionary as a classification task, but they're not really meant for that. So it says, however, encoder-based models are less straightforward to directly transfer to text generation task. A text generation task would be image caption. So how would you do that with the encoder? You would say, okay, if this is it, make a prediction, what word describes this picture, right? Things like that, classification. And then you would say, okay, now go at it, more words. Yeah. It's a hack, basically. Whereas decoder models have not been successfully adopted for image text retrieval task. Why? Decoders do what? They keep predicting the next and the next and the next token. They're not exactly the things that you would use for producing vectors that you would use for a search engine, for image text retrieval. They have different purposes. Right? Guys, is this first paragraph, after what we know, pretty much self-evident?
Yes.
Okay. So then we go, and so these are the limitations of the two models. Encoder-based are greater at understanding, decoder, and therefore not good at generation, whereas encoder-decoder-based, if the output is from a decoder, then they are much better at generation and less at creating retrieval, like hidden vector states that are effective at retrieval. Right? That's the idea. So the next point that it makes, which I literally could have been a sort of different paper, a data perspective. Most state-of-the-art models, obviously it's a reference to CLIP, and CLIP starts out there. Most state-of-the-art models, CLIP, ALBEF, SIM, VLM, etc., etc. So by now you notice that, look at the dates, guys, and it's very interesting to follow through the dates. This paper, the V2 was in February. V1, you can anticipate, was a few months before. These things came out in 2021, has been the year of multimodal, isn't it? That's when multimodal took off. Because if you look at it, CLIP here is 2021, and subsequently already enough work happened, and this work also must have happened in 2021 itself. Right? So it says that most state-of-the-art models, methods, pre-train on image text pairs collected from the web. Despite the performance gain obtained by scaling up the data set, our paper shows that the noisy web text is suboptimal for visual language learning. They say that, garbage in, garbage out, and you have a lot of garbage. There's a point they're making. Well, not quite as bad as that, but the web information has a lot of garbage. And if you pay attention, or if you have a method to filter out the garbage, so you have two choices. Either the caption is right, you leave it alone. Or you come to the conclusion that the caption is not right, then you can recaption it, generate a caption. Or you say, okay, this we have no idea, just filter it out. Right? That's the idea. So our paper shows that noisy web text is suboptimal. How can they possibly show that? By fixing the caption and retraining the model and achieving better performance. Isn't it? So one of the consequences of this architecture will be, it gives you a correction machine, isn't it? Caption correction machine, effectively. To this end, we propose BLIP, which stands for Bootstrapping Language Image Pre-Training for Unified Vision Language Understanding and Generation. I don't know where the acronym, let's look at it, BLIP. So B comes from here, L comes from here, I comes from here, and P comes from here, BLIP. Right? Everybody refers to it as BLIP. A BLIP is a new VLP framework which enables a wide range of downstream tasks a wider range of downstream tasks than existing methods. It introduces two key contributions. So those are the contributions we'll pay attention to. Multimodal mixture of encoder, decoder, right? MED. So, well, we live in the world of multimodal learning now. So it is there. A new model architecture for effective multitask pre-training and flexible transfer learning. So at this moment, we take these. This is a factor 5. A MED can operate either as unimodal encoder. So in other words, once you create this multimodal thing, it has both encoder, decoder in it, both for text and images. So you can use it just as a text encoder. You can use it as a image encoder. You can use it as a decoder, right? Decoder means for captioning and so on and so forth. And so forth. Image grounded decoder and so forth. And so one of the new words that it introduces into the vocabulary is, this word is very interesting. And in subsequent papers, you will find people using this terminology quite a bit. And I'll just highlight these words because it has become, after that, a part of the general vocabulary. Do you see this word come up again and again? Image grounded. Image grounded. Right? Image grounded. What does image grounded mean? No, it's something very technical, and we will see in the architecture. Right. The model is jointly pre-trained with 3 vision language objectives. So this statement, parse it for me, guys. What does it mean? With 3 vision language objectives, image text contrastive learning. Have we encountered image text contrastive learning before? Clip, right? So what it says is that when it says the model is pre-trained with 3 vision language objectives, what objective is a synonym for what? A loss function. So basically it means that in the loss function, there will be 3 separate terms that you are optimizing on. Isn't it? One term is the obvious image text contrastive learning. Clip, right? That is fine. Contrastive is your triplet loss thing. Huh? The second is image text matching. Right? So when you match 2 things, that's a new term that we are adding. And the last is image conditioned language modeling. Means, and here the word image grounded and so forth, image condition. You create a language modeling means you create a hidden representation. What is a language modeling? Creating a hidden representation that is not just based on text, but is also conditioned by the image. Means given the same text, T, and an image A, and given the same text, but image B, you would get different results, isn't it? The hidden state that it would lead to would be, let me just call it hidden state of the text given B. These two will not be the same, even though the text is the same, right? So from that, one can infer that into this machine, text goes in and image goes in, right? 2 things go in. So that is one contribution of this paper. And captioning and filtering, that is effectively a byproduct of this architecture, and that's a significant contribution. They call it CapFit. And that's why many people have said that you could literally break up these 2 contributions to 2 different papers. It says, a new dataset bootstrapping method for learning from noisy image text pairs. We fine-tune a pre-trained MLD in 2 modules. I mean, this machine that we make, a captioner to produce synthetic captions given web images. So this is lovely. What if it could just go caption all the web images correctly? Wouldn't that be lovely? Right? And a filter to remove noisy captions from both original web text and the synthetic text. So you can figure out mistakes in the captions and fix it. Wouldn't that be lovely? Right? Not only generate, but you can find the mistakes. Right? How do you find the mistakes if you were to just think about it? You produce your own text and see how far the original text is from this. If it is very far, then you know that you have to pick one. You trust your own machine.
So is this similar to a RAG in some way, where my synthetic caption is a retrieval augmented generation that I produce to feed in for me to get an output?
No, actually, there is no retrieval. See, what happens is that retrieval augments. When you use the word RAG, it's retrieval augmented generation of some LLM is producing some text, not just from its own understanding of the input, the prompt, but also by doing a search and getting some search results from a database, search index, and using that information as additive to the prompt. Like it sort of amplifies or augments the prompt with that extra information and then processes it. Here we don't do any of that. It is all done within the parametric memory of the model itself, parametric capacity of the model itself.
Is that done by like, okay, this image is landing along with all these other images, but the text related to all the other images is very different from the text that was given for this image. So I'll pick the text of the other images as a synthetic data.
No, not really. But but the question that you asked are good thoughts. Hold those thoughts in your mind because they are relevant thoughts to the architecture that's coming downstream. Right? So let's follow through with the architecture. But just take the takeaways is that it's a multimodal machine. It has both encoder and decoder in it. So it has both ability to understand and create language modeling. Language modeling is just, see guys, when you see these big words, right? And that's why I like math. In my mind, what happens is all of this big blah 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 blah, blah immediately becomes symbols. Right. So what all these big words become is a hidden state representation. So I see in my mind something go in images text. You get a hidden state. So okay, understanding. Then comes the generation part. Okay, what is it? It goes to a decoder, it gets generated. Right? Think simple mathematical symbols, it becomes a lot easier. Yeah.
I'm trying to understand what's the difference between these terms, the image text contrastive learning and the image text matching.
We'll come to that. I'll hold that part also. But somehow, yeah, and that's a defect of language. See, mathematically, it's very crisp difference, but when you write it with English language, in many ways, English language is harder to understand. And there's things written in English in our domain, in AI, are frankly more confusing and harder to understand. Because if you look at literally the words, and your point is valid, they sound very similar. Right? Where are the difference? We'll come to it. Mathematically, they are different things. Simply put, they have different loss functions. Right? We'll see that, and and you'll see it in a moment. So, guys, do we see the two main contributions? Contribution number one: it creates a multimodal mixture of encoder decoder. So, text and images, multimodal, both encoder and decoder. Wow, that's something, right? So the next thing is, as a byproduct of that architecture, it will end up with a captioning machine and a filtering machine. It will generate good captions, and it will also be able to tell bad captions apart. Right? Discriminative ability to tell which captions are good and which are bad. So it will have filtering ability. Do you see that? Lovely, right? So now let's see, how in the world do they achieve this? We perform extensive experiments and analysis to make the following key observations. So they make the observations before this. The observations is that we show that the captioner and filter work together to achieve substantial performance improvement on various downstream tasks by bootstrapping the captions. We also find that more diverse captions yields larger gains. So one of the lovely things with that is this machine runs in cycles. You know, you can initially train it with that junk captions and text, right? It will achieve certain level of understanding. You can use it to filter the obviously wrong things. The filter will come in, but then and then you can caption some of those images better, and then you can retrain the same machine again to improve upon itself. Are we together? And at the end of it, what happens is once you have fully trained the machine on clean data that it itself produced, and therefore the word bootstrapping, then for all things that you use it for clip, for example, you use it for many downstream tasks. These things you use it for many downstream tasks. For all of those tasks, the performance will go up of this machine. Are we together? That's all they're saying. Then it goes on to say, Blip achieves state-of-the-art performance on a wide range of vision language tasks, including image text retrieval. So remember, retrieval is generally the domain of encoders, right? So it says Blip achieves state-of-the-art performance in encoder tasks also. Image captioning, that is a generative task, decoder-like task. We need a decoder for that. And visual question answering, it turns out it's good for that. And visual reasoning and visual dialogue. Oh, that's quite a bit. Imagine you are able to reason with images. This machine can reason, right? And before I go into the architecture, because it is getting a bit too theoretical, let's go and see the results. So, by the way, I must tell you that all research papers are written in this format: introduction, right? Related works or background, method, intro, method, results, conclusion. right? And references. So we just did the intro. Related work obviously is obligatory to say what everybody else has done. Method, we'll come to the method. So you notice that we immediately get into the related works, except that in the intro, they have also summarized the key results. Right? Now we'll go deeper into the results, and then we'll come back to related works. Let us just skip it. We'll go to the method in a moment. But let's go and look at the results. And I hope the results would be, I mean, if you haven't seen something like this should come as quite a surprise to you. Well, we live nowadays, everybody uses ChatGPT, etc. So maybe a little bit too late to get surprised. But now you know what engines work behind those machines. Right? Look at this image. Somebody has given it a caption. The red is the caption that somebody has provided. From bridge near my house. Very meaningful caption. The person was trying to remember the scene from some bridge near their house. But is that caption truly descriptive of this image? Is it aligned to the image? No, isn't it? And now see what this architecture gives it as a caption, generates as a caption. Would you agree that it's a far superior result? Right? A flock of birds flying over a lake at sunset.
So on the context, right? So what the user was trying to say is or her perspective when they posted that image on his social
That is right. That is right. No, but see, your question is, if you create a database of images for training other machines, then that caption is not very meaningful. It is meaningful only to the user.
So Blip is making it more context relevant for its own self.
Yeah, for the image. It is aligning it to the image. The caption, so the question that we are asking is, does the caption describe the image?
Okay.
Right? So the former does not describe the image in a general sense. It describes the image only for the user, but not in the general sense. But if you look at this caption and you stare at this image, and I invite you to stare at this image, guys. I don't know, but aren't you surprised? Like, do you realize that 3 years ago, all of these things were not possible? It knows that they are birds, that it's a flock of birds, that it's flying, and there is a lake and there is a sunset. You see how much it is understanding the image.
Yes.
Right? The color me impressed. Okay. Likewise, let's look at the next one.
If I'm sorry, Asif, again, like, so we're talking about the curated message. The TS is also an input that is being provided, right, to the filter.
No, TS is the output of this machine. It is saying that the input, the one that was given, is not as good. Here is a better. Here is my description of this image.
Okay.
The TS is the machine's generation.
So the S here is suggested and not similar.
Come again?
The S here means suggested and not similar.
No, suggested is what the machine is suggesting as a better caption. Right? Is generating.
I thought the synthetic text was also an input to the filter, which then decided between the incorrect one and the correct one. But you're saying that's machine generated, because when we were talking about this just a few minutes ago, I thought the synthetic text was also.
No, you can use it too. Yes, you can use it too. See, the steps are this. Here's the pipeline. You generate a synthetic caption. Then you can ask, exactly to your point, is the synthetic caption that you generated caption, is it a significant departure? Is the vector significantly departing from or dissimilar, this text, from the original caption, the web caption? W stands for the web, right? And if it is a departure, then what can you have to trust one or the other, right? So you say that my machine is right and I don't trust the web caption, so let me filter it out. Right? So the filtering machine will basically say that, hey, if you're too dissimilar from the synthetic caption, then I'll weed you out. Does that make sense?
Yes.
So the first stage is you use the machine to first generate the synthetic caption. All right. And then the discriminative task.
Model.
Come again?
That's why support to have a pre-trained model.
Yeah, this model, the good thing with this model is you sort of feed it a lot of data and it continuously does this process. And therefore the word bootstrapping, the B in this, it improves itself, it does a better job, it creates new data to retrain itself. So it's very beautiful. It basically creates data to train itself better, right? And you see one of those architectures where the machine says, hey, I can make the input data better and improve myself.
But is that an automatic process?
Yeah, and we'll go through that.
So the word supervision is like
Come again, the BERT supervision?
the supervision, the word supervision was there, right?
Supervision just means supervised learning.
Correct. But so let's say, for example, I'm passing through that the learning cycle. If somebody is like looking at the result and correcting it.
No, it is not somebody.
Only by means of gradient.
Yeah, see what happens is you start with label data, no? Okay, guys, you guys are getting very confused. So let me start again. Let me draw it out again. Guys, from the web, what do we get? We get a lot of images. Cat. And cat on the window. So what am I getting? I'm getting an image I and a text I. I get this pairs. Do we agree with that?
Yes.
This is my data set. I call it the web data set in this paper, W. Right. Now, what was CLIP? CLIP does contrastive loss and can train. It just assumes it to be the gospel truth. Whatever caption comes with images, it treats it as gospel truth and trains itself. And as we notice, it does a pretty good job. You saw it in your Jupyter notebook for search. Does a pretty good job. This paper says, no, wait a minute. We notice that this guy is very noisy, very noisy. Lots of mistakes in this data. Okay, leave that aside. What this paper also says that, see guys, there are models which are good at the encoder part, with the understanding part. There are models which are good at the generation part. Let us create a new architecture which has two qualities, good at both understanding as well as generation. Are we together? How it will do that, we'll come to it. The second thing it does, and which is getting you guys sort of confused, is as a byproduct of creating this machine, what can I do? It can create a captioner and filter. How will it do that? Let's just reason through it. It is just common sense, even without thinking about the architecture. If I have a machine that, given an image, can produce a caption out of it. If it can caption this machine, then image, right? So it will produce a synthetic caption, right? So that is the generative part. So I have a captioner. I have therefore a captioning machine. No brainer, right? It's a generative. It can, given an image, it can produce a caption, right? Text, and that text will consider to be the caption. But then there is a discriminative task. What it can do, you can take TS and TW, the TW being the original caption from the web. And what can you do? You can train a machine to say if these are very different. See, you can look at the difference between the two, and you can have a certain threshold. And you can say if the diff is greater than this, I say throw it away. I mean, basic classification task. This becomes a classification task, right? Is this caption good or bad? The original caption. Do you realize that this is a simple classification task now, right? This machine says, I have a caption. There's an original caption. I compare the two, and I therefore come up with only one decision. Original caption, good or bad. I can do that now, right? Why can I do that? Because I have something to compare it with. which I consider to be the ground truth.
Yeah.
The machine will trust itself. And therefore, because of its ability to discriminative, this discriminative ability gives it filtering capability, right? It can filtering capability, filtering of bad images, bad captions, sorry. So you have a choice. You can just filter out the bad captions, right? If you so choose, you can say, hey, see, look at this. Given an image A, text, the text that came with the image, there are only three possibilities. Either it is good, you determine that it is good, text is good, right? Why is the text good? Because you compared it with your own generated text, right? So you say, I'll leave it alone. But if it is bad, then you have two decisions to make. You can throw it away, that is the filter, or what you can do is keep with new caption. So you create IA and the A is replaced with the synthetic caption, right? The original web caption is thrown away and you replace the data, the same data point with this, right? So what happens? You have just improved the quality of your data set.
Distillation?
It's not distillation. I mean, it's distillation in the classic chemistry sense, but in machine learning, distillation has a different meaning. Right? It is data cleanup.
But don't you need a human to make the decision
No.
whether to throw?
No, so typically what happens is when you do it at this scale, when you have 100 billion images, bringing in human beings is not cost effective. Right?
So how do you know if that's the right thing?
Yeah. So when you're training, you take a few samples and see whether it's doing the right thing. And what they found is that when they trained this machine, it worked so well. See, you try it on small samples. That goes through human review. Some scientists would sit and review it, and they will say, "My God, this machine is doing much better than the original captions." So, guess what we should do now? Let it cycle through all the original data set, and clean it out. So once it cleans it out, you ask the second question that immediately comes is, okay, now that we have a clean data set, can we not improve this machine all over again? Right? And you feed that data set back into the machine and further train this machine.
So in the real world scenario,
yeah,
for the smaller data set, somebody will be looking at the results to make sure that okay, the machine is doing the right job.
Yeah.
Or I need to kind of do something else.
That's right.
So that I need to do
it,
right?
You do that. You take samples and you do careful review of that.
Right. So that's why the supervision is committed.
That is right. Yeah. See, supervision is whenever you have an output, machine produces something that you can compare to a ground truth. That is the meaning of supervised learning. Okay, guys. So are we clear? Is there any further confusion? Way back there.
What is the keep the other data set with? So you said very often, right? You throw it away or you get the other caption. So
the reason you would throw it away when you produce a text, generate a caption about an image. What happens is that it gets a little mathematical. You produce it, you have a certain confidence in your own caption, right? When you are not confident about what you are seeing, right? Like, so it says, maybe it's a lake, right? Then you don't want to keep that data point anymore. It's not sure. Machine is not sure. You would rather filter it out, right? Whereas if it very clearly says, I see a flock of birds flying over a lake on a sunset, and it says, I'm pretty confident about it, then you keep it. That's how you do it. Yeah, that's what you do. When you keep it with the new caption. Right? You say that the old caption was no good. I'm going to use the new caption. So guys, are we together so far? Right. Now let's look at the second example. In front of a house, door in Reichelfeld, Austria. It gives you the context of that image, but doesn't tell you much about the image itself. In front of that house door in Richelfels, Austria, could be a car, could be a horse, could be a person standing. You have no clue what is there. Right? So would you agree that the second caption, the machine generated caption, is better? This is better, right? And in the third image is a little bit, that's where you realize that sometimes the original context is better. The current castle was built in 1180, replacing a 9th century wooden castle. Right? So, well, that's quite a bit of history associated with it. The fact that the machine is seeing a large building with a lots of windows on it, right, actually diminishes the information there. It is a better description of the image, but you lose history there. So they are giving it as a counter example where
in the second image, I almost feel like it could have taken the place Reichenfels Austrian put it in the image.
That's right. It could have just augmented the caption. But the way these people do it is that at this moment, they just said that this is a case we would reject our own caption. Right? So anyway, then...
As a quick question there. The first and the second makes perfect sense, okay? Because the model is interpreting what is on the image and it is getting the information. But then on the third one, how does the model even know that is relevant to the picture that's provided? 1180 replaced with a 9th century wooden castle. How is that possible for it to like for the filter to say that that is right?
That is a very good question. And for that, you have to understand the architecture. We can actually. Right? So we'll come to the architecture in a moment. Huh? Right? I'll give you a very succinct answer to that. See, the fact that this is a castle, right? And the fact that this text is about castle, when you do the embedding, they land very close to each other. Right? And so you will realize that the generated text is actually departing significantly more from the image than the original text. And you keep the original text.
So the large building is
yeah, because large building could be the White House, right? Or it could be one of the Google buildings or whatever it is, right?
But who keeps the original text? The system?
Who keeps me? Everything is stored on machines. We always keep the original data.
But then, I thought the logic was if there's a lot of loss, if the loss exceeds a threshold, then we keep what we do.
Oh no, by keeping we substitute in a new data set. We never get rid of the old data set. It's just that we are generating a new data set in which we have done a substitution.
Okay. But even in the third image, there is a danger, right? Yes, it is about a castle, but you don't know if it's specifically about that castle that was built in 1180, right? You're trusting
you're trusting the caption. See, sometimes these are judgment calls, and at the end of that, you have to know that yes, it's true. No machine learning algorithm, especially the ones that work at such massive scales, you don't shoot for perfection, as the American saying goes, right? Let perfection not be the enemy of the good. This machine achieves things that were hitherto impossible to do. People couldn't do. A little bit of loss of accuracy is the fact that it's not perfect. It's okay.
Just the representation of the image, not that the context.
Yeah. So guys, let me show you a few more images somewhere down there, and then we'll talk about, so this paper is quite involved, and I would like to go through the architecture before you guys go for lunch. I know you guys can all smell the lovely lunch. Thank you. So, okay, look at this thing. Examples of the web text and the synthetic text. Greens are accepted by the filter. So, good thing is that the filter actually knows when its own generation is not good. Right? At each situation, tell me if the filter made the right decision. Let's look at the first one. A week spent at our rental beach house in Sandbridge. The other one is an outdoor walkway on a grass-covered hill. Do you think the filter made the right choice with the green?
Yeah.
It's a better description of the image, right? Especially when you are going to use that caption to train models. The first caption is not very useful in training models. The next picture, a car is driving past a small old building. Surely, from a machine learning perspective or as training data, the second caption has more value. Right? Whereas the first caption hardly says anything at all. That's what a sign says over the door.
Yeah. So our captions are saying what the person feels about.
Exactly.
Not. But,
and sometimes it can be wrong. Like, for example, look at the image on the bottom left. Stunning sky over Walnut Island, Lake District, July 2009. Lake District is, of course, there. Now, if you look at this picture, you would agree that the original caption was actually far better. But the synthetic caption is actually wrong. Right? And yet it was picked up. So it's an example of a mistake. Right? That no machine learning algorithm is perfect, of course. Let's look at the next.
First row, second one, the middle one. Is there I can't see what the sign says, but that's a lot of things in that image, right? There's two cars, so we have to get the right intent that image, right?
That is right. And see, think about it this way. If your job is this, forget how and where the image came from. You have to describe this image. Because you're going to use image caption pair for downstream machine learning tasks. Would you prefer the second green description or would you prefer the first one?
No, that's why that image, it can be, I mean, it says car and a building. But I mean, for me, it's a bit.
It's a bit generic. You could be much more specific. And as you will see, blip is not the end of the journey. We are going to go and cover more algorithms, which will do far better than even blip. So by no means am I claiming that blip is state of the art. In fact, remember that I said today we'll do blip 2 and lava. Guess what those things will do? We brought in clip, praised it, and then we toppled it. And then we went to blip 2. Blip, right? So as you can imagine, the progression is there. Right? So we will come up with better and better description of the image. But as of now, if all you know is clip, would you agree that we are getting better? See, I'm taking you on a journey, guys, multimodal journey, right? We are not there yet. Look at the moon, a handheld, etc., etc. Obviously, the text generation is much better. The pink rock from below. Some colorful trees on the hill in the mountains. By the way, this is very, for me, nostalgic. I used to live in Northeast and these beautiful fall colors used to be very common. In California, I missed that.
So, Asif, can I ask a quick question here?
Yes.
So, many times there is metadata about the image itself, not just a description. Like, for example, what kind of camera you take it with. For example, and as a photographer, for example, they'll say, okay, what camera created this kind of a picture? Canon say D70 or something like that, for example. Those kind of things. And the other thing is about location. Two buildings and two different locations could have similar kind of patterns, but the location will make an importance here. Right. So those kinds of metadata is being lost by plain description of the image itself. Because in a context, those metadata could be the difference between the right image and wrong image.
Right. See, Gopal, that was lost long ago. See, what's the journey? Somebody has an image with metadata, uploads the image in low resolution because you never upload on a website high resolution images. So you downscale and put a web optimized image.
Okay.
All metadata is gone. The guy may or may not put a all text caption there. That caption may or may not be meaningful, right? So by the time you get the data, which is meant for clip and all these tasks, that data is in a pretty sorry state already, right? It's a low resolution image.
Okay, got it.
It is just caption. And what this machine is doing is already improving upon it.
No, the thought I had was there are a lot of this auto tagging that the photo can have, right?
Yes.
So if those things are there, will this blip override those information?
No. It doesn't. See, remember, machine learning algorithms almost never override. They just read an info. So it may come up with its own inference. The green are these inferences it's coming up with.
Okay.
So,
okay. Thank you.
So guys, I know it's getting lunchtime, but I would like to finish. It's getting a little bit late, but I would like to finish this architecture now. So what is this magical architecture that's able to achieve all of this? Worth studying, right? I hope the results are compelling enough for you to see the architecture. And the architecture is actually quite interesting. Look at it carefully. So this architecture, I call it as 4 pillars, because then it will be easier to understand. Pillar 1, pillar 1, pillar 2, pillar 3, pillar 3, pillar 4. Right? So let's look at it from the 2 outer pillars, 1 and 4. The first pillar, what do you notice? What do those white lines crisscross imply? They are reminiscent of what?
Patches.
Patches, VIT, right? Yeah, exactly. And so what are you doing? You're passing it through an image encoder, and in particular, a transformer-based image encoder, not a CNN one. And what is it producing? It is producing a hidden image state, image, which is going to something. Oh, there is a contrastive, image text contrastive. So this is image text contrastive loss. So there is a loss term that compares the text encoder. Now there is a text encoder. You notice that there is whatever text, original caption that went in there, a little girl holding a kitten next to a blue fence, that goes into the second pillar as it goes. So at this moment, there is a cross attention. Just ignore that fact that it is even there. This is your standard encoder, right? Do you notice that attention is there? You produce a encoder vector. So this and this coming together, if you look at only the first and the second pillars, what is this? This is clipped. And literally this is the ITC is the loss function for clip. So we have clip there, all right. Let's leave it there. Now let's look at pillar 4. What is pillar 4? Pillar 4 looks suspiciously like it's basically a decoder, right? Isn't it? You feed in the original text and you ask it to generate more text for it, right? Completions. And what you do is, and this is the part that is very interesting, you are giving it the hidden state of the image. Here, you notice that the image encoding is being given somehow, being injected into the decoder. Like, it is not an ordinary decoder. You're doing something weird. You're throwing in the hidden state of the image. And by the way, that hidden state of the image is also being thrown into the third pillar in between. Right? When you do that, there is a term called, and this is a new term you guys are encountering, this is the cross encoder. So what it means is that, remember, you do the attention between 2 vectors in a sentence word, for example, you give it 2 sentences and you look at attention between those things, right? So here you're doing, in a way, one sentence is the one coming from the image, another is coming from the text, right? So you are doing cross attention between that. And when you do cross attention, the thing that you bring in from the side, like, is called the grounding. You are saying that you are image grounding. This is the image grounding that you are doing. This and this are the image groundings that you are doing, right? So what happens is that the first and second pillars are your traditional clips. The third pillar is interesting. What it says is that I'm going to take the text, but as it makes its way upwards through the encoder, somewhere in between, I'll sneak in. It will have to pay attention to the image encoding vector. Are we together? It will have to do cross attention to that. So it is not a simple text encoder. It will come up with some result here. Then there is another loss function that is here. That is the image text matching loss. This is image text matching image text matching loss, right? Now, how aligned they are, right? Matching loss. Now, image text matching loss you can do using a very simple, for example, cross entropy and loss, right? So I expected this. What is this? So exactly, this is it, and we'll talk about it. It will go there, and finally, you have a third loss function because this machine is going to generate. So if this is the decoder part, what will the decoder do? Decoder is the generative part, isn't it? It's going to generate its own text. But when it generates a text, it is getting the original text, but it is getting the grounding. It is getting the cross attention from the image. Do you see this, guys? So this machine is going to also generate its own text. When it generates its own text, you have a generative loss. Text generative loss means I expected you to produce the word cat and you produce the word dog, right? So no, I don't like it. What's the probability of your cat? Low? No, not good. Okay? So that's a loss in the generative side. So we have three loss functions. Do you see the three boxes that I've circled? The image text contrastive loss, the clip traditional loss, image text matching loss. You say that if I'm doing contrastive loss, then why am I doing matching loss? They found that actually, if you throw in a standard loss function, the traditional loss function, it helps, right? It just makes it better, and you'll see why in a moment. And then, of course, if you have a decoder, then you better, how in the world will you train your decoder unless you have a decoder loss term, the traditional decoder loss term? So they throw all of it in, but these would have been independent pillars. What's tying them together? The contrastive loss is aligning the encoding of the image to the text while you're training, but then that image ground becomes the grounding to the two right pillars, third and fourth pillar, right? So now let's work our way through. Can we use this machine to generate? Can I just give it a text and nothing? Just give it an image and not give it a text, just a blank text? Of course I can, isn't it? I could. In that case, what will happen? Machine will still generate something. That will be my caption, right? Now, what can I use the image text matcher for? Suppose I give it a text and an image encoding image. I can see to what level the image and the text align. If they don't align much, I can say, well, I don't know. Do I need to filter this out? Isn't it? I can use, and that's the purpose of this. So that is this architecture, guys. So this is interesting architecture. As you can see, it is attention. The new concept is cross attention, the image grounding. But other than that, it is your classic transformer. So, but with repetitions, with lots of repetitions in there. Yeah.
So in a way that, let's say, for example, I'm scraping the web and throwing away all the captions, whatever I have, just to fit that only the image, then I should be able to generate the description.
Yeah, today people do that. See, what you can do is, first the question is this machine trained? Like once machines are trained and you download it from Hugging Face. Right? So Salesforce, by the way, this work comes from Salesforce. They have obviously given it over to Hugging Face. You can download it. This is an exercise you guys will do in your project. Download it from Hugging Face, and then you get an image. You pass your image through it and ask it to generate the caption. Beautifully, it generates a caption. So it's therefore a captioning machine, and it does a pretty good job. Can something do a better job? Yes, we'll see. Right? So this is a progression in the journey to multimodal language understanding. Right? But this is a huge milestone. When Blip came out, it was a huge milestone. Right? You have a question?
Yeah, one question is, the encoder-decoder architecture, part of the encoder feeds into the decoder, right? But I don't see pillar 3 feeding into 4.
No. What is happening is, think about it this way. Pillar 2 is improving the result of pillar 1 because of the contrastive loss, image text contrastive loss. right? During the training process. At the end of it, what is feeding into the decoder, right? You know, from the encoder, first three pillars are encoders, effectively.
Yeah.
What is feeding from the encoder to the decoder is only the language representation of the image, just the image grounding. So it is going, H is going, remember?
I see, okay.
H is going.
If the model is present in Hugging Face,
Yeah,
is it like,
pre-trained, yeah.
I'm trying to ask them, is it available for anyone to use?
Yes, of course. Of course. Use it. In fact, you will have to use it to do this bootcamp.
Yeah, for the bootcamp, yeah. Just trying to understand.
Yeah.
My work perspective.
You will love it. I mean, see, guys, these are things, shiny new toys that have come up only in the last couple of years. If you had asked somebody in 2020, are these things possible? And when will it be possible? Right? Or 2018, if you had asked this question, seriously, they would have said maybe in a few decades. And suddenly it all became possible. So, all right, guys, so that is this paper. Any other questions? By the way, was it reasonably clear? Did you get a sense of what this is about?
This makes sense after the flip architecture.
Yes, yeah. So natural progression after clip. So after this, guys, in the afternoon, here's our plan. I won't be able to do two papers. I'll just do blip 2 because it's a natural progression. I'll stop there, and then we'll go into the code, like we'll go into the coding part. I'll walk through some of the partial solution that I gave. Does that make sense?
Yes.
Okay. So with that, I'll stop the recording, and I wish you guys a good lunch.